going to talk about, try to introduce what pulsars are, try to introduce what we think of as the main basic properties of pulsars. And today's lecture, I'm going to try and focus on how it is that we know the particular details about pulsars that I'm going to describe. In other weeks, I'm going to talk about more specific details about pulsars, how pulsars have been used to test Einstein's theories of relativity, for example, and some current sort of exciting stuff that's happening in the field. But today, we're just going to set the stage. So I hope all my buttons work. Okay. So what I have listed here is what I think are like the 7 or 8 things that everybody kind of agrees a pulsar is. And so today's lecture is going to be talking about these 7 or 8 things. But before we look at that, I want you just to look at this little cartoon. And this is really what we believe. This is not such a simplification. This is really what we believe a pulsar kind of looks like, which is a very dense ball that has radiation which comes outwards in like a jet-like beam. And because this ball spins around, every now and again this jet-like beam will be pointed at the Earth, and if you happen to be looking at the sky with the right kind of telescope, you will see that flash from that spinning ball. And this is sort of the signal that you would see on your telescope. It would be a repeating pulse that sort of is low and then rises and then falls again. And it's just a very regular, very precise pulse that appears almost as if it was man-made, almost as if it was like Morse code or some digital signal, but in fact it's made by a spinning star called a pulsar. And so now I'm going to go through the list of what we think pulsars are. So they are observed as periodic sources of pulsed emission, typically in the radio. They're most commonly observed as radio sources. They're born in the aftermath of a supernova explosion. And they rotate with periods which last a few seconds to a few milliseconds. Shockingly, they contain about 40% more mass than the sun to 2 times the mass of the sun. So they're very, very heavy. And they have the highest magnetic fields that we know of anywhere in the universe, reaching as high as 10 to the 15 Gauss. Probably the most shocking fact is that this object, which is 40% to 100% heavier than the sun, is squeezed into something 20 kilometers in diameter, so something about the size of Chicago. And this we call a neutron star. And despite some complications, a neutron star is essentially a big ball of neutrons. So to approach the first thing, which is that it's a periodic source, I thought what better way to kind of show that than to just look at the data. So this is a particular pulsar. This is its name, PSRB 0329.54. It has a period of 0.714 seconds. So that means it spins about 1.4 times a second. And if you had a large enough radio telescope and you connected your telescope antenna output into a speaker of your hi-fi sound system, then this is what this pulsar would sound like.
Quite a different intensity.
This is just this is where you notice some of the pulses are not as intense as the other, and this is a feature of the source itself, of this particular source. This is another pulsar. This is his name, PSRB 1055-52. This is a shorter period, only 197 milliseconds, and this thing spins at about 5 times a second. So remember, we're talking about something heavier than the sun, squashed into something the size of 20 kilometers, and spinning 5 times a second. And if you have the right kind of radio telescope, you can point it up and listen to these guys. All right. How about this fellow? This is a very famous one. This one is called the Radial Pulsar. I work a little bit on this pulsar. Its designation is PSRB 0833-45. It has a shorter period again, 89 milliseconds. So that's about 10 times a second it spins. So it sounds like a helicopter or something like that. But it's something is heavier than the sun, squeezed into something the size of Chicago, spinning 10 times a second.
Are the
the record breaker.
Are the amplitudes in all of these equivalent?
No, there will be some variations, but this is a very bright one. So this is the fastest one you're going to hear today. It's not a very nice sound, but it is the fastest one that you're going to hear that I have today. It has a period of only 5.75 milliseconds. It spins 173 times a second. So again, something as heavy as the sun, or heavier than the sun, squeezed into something the size of Chicago, but still spinning 173 times a second. So this is a very extreme object. The fastest one we know of today has a period of 1.4 milliseconds, which means it spins 5 times faster than the previous guy, 700 times a second. That's the record holder right now. And so I think I've convinced you, just with looking at the raw data, that we have a periodic source of pulsed emission that's typically observed in radio. So I give myself a little green check mark there. I think just by looking at the data, we can all agree on that.
Can we observe these only because we're in the beam?
We only are able to see them when the beam's pointing at us, correct. So now I'm going to talk about in great detail next week. Next week is going to be about this fact, that they're born in the aftermath of a supernova explosion. And what we believe happens is you have a very massive star that collapses in on itself. And when it collapses the core into the dense object, which we're calling the neutron star, and the outer layers get blown off in a big supernova explosion. And so when you look at what we call the supernova remnant, you'll see sort of the shell of the explosion with the dense neutron star source in the middle. And when we go and look at these pulsars in radio telescopes, what we find is that they're sitting in the middle of these remnants. And that's how it is that we know that they're associated with the remnant. So this is an example of a supernova 386. You see here this nice optical image of the shell, and you can't see so much, but there's a different color in here that's blue. It's just somebody colored in the X-rays from this image are blue. And if you take these X-rays and you look at them in a series, you'll see that they pulse up and down. So this is an X-ray pulsar where if we look at it, we can see an X-ray beam pulsing at us, and this fellow has a period of 65 milliseconds. Another example, this is called the Guitar Nebula. I don't know if people can see so clearly, but you have sort of the shell of the remnant here, and then out here the pulsar, this pulsar PSRB 2224 plus 65, this is how it looks in the radial pulse. And he lives right here at the top. And what's happened in this example is that the explosion had some asymmetry to it. For whatever reason, the material didn't collapse exactly as a sort of a centrally dominated influx. And so the neutron star was sort of born with a bit of a kick. And so it has been kicked out of the circular shell, and we can follow this across the sky. And if you kind of measure the velocity that this fellow is flying away, and you sort of rewind the tape, you'll find that at the very time that this shell was at the center, this pulsar was at the center. So this is an observational fact about pulsars, is that sometimes they're seen in the center of the remnant, and other times they're seen shooting off to one direction with high velocities, kick velocities they're called. So as I said, if you're interested in this particular aspect, show up next week. Now, how about this fact, that they're rotating with periods lasting a few seconds to a few milliseconds? Now, I've already put a green check mark beside there because I think you will agree with me that the thing happens on the time scale of a second or a few milliseconds. We've seen that. I've underlined here, why is it that they're rotating? How is it that we know that we're dealing with a rotation and not a pulsation or a vibration? So why are we sure of that? And so when we look at the sun, this is just an image I grabbed off the web of the sun and the relative size of the Earth. So at the equator of the sun, the material at the equator does a rotation about once every 25 days. So once every 25 days, something as big as the sun manages to do a full rotation. Now, the diameter of the sun is about 1.4 million kilometers. So if we take, say, the core region, which I've just said, for sake of argument, is about 3% of the diameter. So the inner 3%, that has a diameter of 40,000 kilometers. If we were to take something like that and squeeze it into something 20 kilometers in size, we still have to conserve momentum. So we're taking a very wide, very heavy thing, and we're punching it into something very small. And so what you'll all know from looking at a skater, when they're nice and wide and their arms are wide out, they're spinning slow, but then as they move their body closer and tighter, their spin speeds up. So conservation of angular momentum is what gives these giant stars a high rotational velocity when they're punched down. And so people don't necessarily have to understand anything beyond that, but if you just do the numbers, this is an expression for what the angular momentum is in terms of the mass, the radius squared, and omega, which is the rotational frequency. And so, as I said, the simple example I gave, if it goes from 20,000 kilometers down to 10 kilometers in radius, then the r squared term, it's squared, it's 4 times 10 to the 8 squeezed down to 100. And so that's a shrink of about 6.5 orders of magnitude. So if we're going to conserve conservation of momentum and we shrink the r squared term by 6.5 orders of magnitude, we must increase the rotational frequency term by 6.5 orders of magnitude. And so that expression that I gave you, that something will rotate about once per 25 days, if you shrink that by 6.5 orders of magnitude, you get a rotation of about once every second. So that's perfectly, we can easily spin up a neutron star to that velocity just by taking a slow-moving wide star and compressing it down. Stellar vibrations, which we do see, and stellar oscillation modes are much too slow. Further, and something we're going to talk about in future lectures, is that pulsars are seen to slow down. Their rotational velocity is seen to slow down, and so this slowdown is consistent with the loss of rotational energy. So I give myself 2 check marks there. We have.
How slow?
How slow?
What's the rate of deceleration?
It depends on different pulsars slow down at different speeds. We'll talk about that in much more detail in other classes. Now, how about the mass, all right? How is it that we know that we're dealing with something 1.4 solar masses to 2 solar masses? All right, now what I've plotted here is, so this is a radial pulsar, and it's plotted twice just for easy viewing. So you can see the first pulse and then they've repeated it again. Now, what I'm showing in this plot here is essentially that pulse every time. So time is on the y-axis, and the sort of brightness of the pulse is on the z-axis, and the phase of the pulse is on the x-axis. And so you can see this sort of black streak as every time if we wrap around, and the place where the intensity is in the same place. So this is how a typical pulsar will look in this diagram. Now I'm going to show you this guy. So I have a bright person in the room who is going to tell me what's happening to this pulsar. What is it? What's happening with this fellow is he is in a binary system. Okay? So this pulsar isn't just spinning around by itself, it's also orbiting another star. And so sometimes, because of this orbit around the other star, sometimes it's moving towards the Earth, and other times it's moving away from the Earth. And so because of this, we see the pulse arrive a little bit earlier than we expect sometimes, or a little later than we expect at other times, because of this relative motion in and out. This is simply the Doppler shift of the pulse because of its motion around the common center of mass of the 2 orbiting bodies. So by measuring how the pulse moves, we can measure exactly what's happening in this binary system. We can measure exactly how the orbit of the binary system is happening just by correcting for the arrival time of the pulse. And when we correct for the arrival time of the pulse, we get something that looks like this. Now, this data is exactly the same data set as this data here. It's just spread over a longer period of time. So can anybody Give me a reason why they think there might be large gaps in the data equi-spaced.
Shade each other.
It's exactly right. It's an eclipse. So the pulsar in this case, he's happy we see him, and then he has gone behind the companion. And he's eclipsed by the companion, and then he comes back out from the companion again. And so because we understand gravitational orbital motion very, very well, by measuring very precisely what's happening in this orbit, by seeing how this Doppler shift happens, we can then learn exactly how these two objects are orbiting each other. And from our standard knowledge of Kepler's laws and so on, we can measure the mass. And we measure very accurate masses. So this is one of the most accurately measured numbers of pulsars that we know of. And we know this from binary systems. And in week 4, we're going to talk a lot about also binary systems. How am I doing? How am I doing on time? Am I gonna? 18 minutes. Okay. All right. So we're moving fast. You're learning a lot. All right. Now we're going to get into maybe things that are a little more difficult to explain, but I'm going to do my best. How is it that we know that they're so highly magnetized? So I told you that they can measure, we've measured magnetic fields 10 to the 8 to 10 to the 15 Gauss. How is it that we can measure the magnetic field of something like this? So it's a little bit about the same argument about the conservation of angular momentum. In the collapse, if you conserve what's called a magnetic flux, then you get pretty close. So the magnetic flux is the magnetic field strength multiplied by the area. And so that's the surface area of the star. And so the surface area is 4 pi r squared. And earlier on, we showed that the r squared term shrinks by about 6.5 orders of magnitude. So in order to conserve the magnetic flux, this B term must increase by 6.5 orders of magnitude. And so B would grow from about 3 times 10 to the 5 Gauss, which is the sort of magnetic field strength you would see in the core of a dense star, of a massive star. And so we can easily bump that guy up to 1 times 10 to the 12, just by conserving the magnetic fields, the magnetic flux. So because we're shrinking the area, we have to sort of concentrate the magnetic field. And so magnetic field strengths come out naturally from the collapse scenario. All right, that's one check mark. But we also have other objects, other binary objects. So this is an example of what I'm calling a high mass X-ray binary. So this is a situation where we have our pulsar, we have our neutron star. The star that it belonged to has long been blown away. But there's a binary, one of its neighbors happens to be a massive star. And after a certain amount of time, when these two guys are orbiting each other, after a certain amount of time, the material from this star can fall on to the neighbor. Just gravity from the neutron star will pull in material off this fellow, and it will land. And so now we have our neutron star, but we have an atmosphere, a very thin atmosphere around the neutron star that's sort of made of regular star stuff, gas and so on. Except that this gas has now been pulled over, swirled around, and fallen on. And so this type of system has a lot of X-ray activity. They were observed as X-ray flares. In the 50s and 60s, a lot of these X-ray binaries were discovered. And so we can look at the X-rays that are coming off this thin atmosphere around these neutron stars, and we can look for cyclotron resonance features. This is a feature where an electron orbits a magnetic field, and the period that it orbits the magnetic field has to do with the strength of the magnetic field. And so this is a feature we can see in X-ray spectra. We can see these X-ray absorption features that correspond to cyclotron resonances, and that tells us what the magnetic field strength is. So, So this is an example of, this is not a very pretty plot, I apologize, but this is an example of what the X-ray spectrum would look like from one of these sources. This was recorded by a space telescope called NuSTAR. And what we see, if we look at just this panel here, we see this very obvious fall and then rise again. And this occurs at 30 keV, 30 kilo electron volts. That's the peak energy of this valley. And if you plug 30 keV into our cyclotron formulas, then we come out with 10 to the 12 gas. So there's many, many cases where this same resonance feature is seen in X-ray binaries, and it's interpreted as a cyclotron resonance, and it gives us the only direct measurement of the magnetic field strength. Okay, now the diameter. The most shocking fact of all, I guess, that this is such a heavy body, but it's been collapsed into 20 kilometers. How is it that we know that? So, what I want you to think about now is, let's think about what the largest diameter it could be. Okay? So let's think about if we're going to say, all right, let's imagine a particle of the surface material, like a small little particle sitting on the surface of this neutron star, spinning around. And what we do is we say, okay, as it spins around, there's going to be a centrifugal force that's pushing it away, and it's being held on by the gravitational force. So if the crust is just about to break away, if it's just about to disintegrate, what radius does that happen at? Okay, so if we equate the gravitational force with the centrifugal force pulling out, so this is the centrifugal force, this is the gravitational force, you see the radius is in here, and then the period is 2 pi divided by the rotational frequency. So if we rearrange this term, if we rearrange this equation up here, then we can say that the r, the radius, when you balance centrifugal force with gravitational force is this expression here. And so, if we put the mass of 1.4 times the mass of the sun, and the period of the fastest known pulsar we have, which is 1.395 milliseconds, this is this pulsar here, then the maximum radius we get is 21 kilometers. So that's the radius. So that tells us that if the radius was larger than 21 kilometers, this object would pull itself apart. So this tells us that the radius has to be less than 20 kilometers. Okay? So this is a most startling fact already. Even though it's actually the diameter that's 20 kilometers, we already know from very simple arguments that it can't be larger than 40. The diameter can't be larger than 40. I just wanted to point out that this pulsar was discovered while I was at McGill by a grad student friend of mine, Jason Kessels, in 2006. This very fast spinning pulsar that holds the record, 716 hertz. So there are other ways that we can explore the radius of the neutron star, and that's by exploring these binary objects again. These binary objects that have material from some other source living close to the surface of the neutron star. This material can radiate emission lines, and the emission lines are redshifted. Because the neutron star is so dense, it actually warps the space-time around it. And so a photon which emerges in this space-time is going to know that the space-time is warped. And then as it emerges from the space-time, the frequency of the photon changes. This is called gravitational redshift. And so what the gravitational redshift allows us to measure is the ratio of the masses. The ratio of the mass to the radius. And so if you follow the numbers correctly, if you put in a mass of 1.4 solar masses, you'll get a radius of 11.4 for a particular example of redshift that's been measured. And so in this case, the diameter we measured to be 22.8 kilometers. So we know from equating the centrifugal force with the gravitational force what the maximum radius is. And then we know from gravitational effects like gravitational redshift, or in the case where we have these eclipses, sometimes, and we'll talk about this in another lecture, sometimes we can see from the eclipse signature when one of the sources is behind the other, we can sort of see a delay as it propagates around this gravitational well, and from that we can also measure the radius. So I give myself a green check mark there. Okay, and so finally, now that these are all sort of observational quantities, finally we have to pin a name on this guy. We have to decide what is this very dense, highly magnetic spinning object. Okay, and so we call it a neutron star, and it's essentially a big ball of neutrons. And you can think of it actually as an atomic nucleus itself. So we know that an atom is mostly full of space, with a very dense collection of protons and neutrons in the center, and then a cloud of electrons outside. So what we can what a neutron star is basically if you take the centers of atoms and you crush them all together to make a giant atom, almost a giant atom. So it has the density, or close to the density of nuclear density, the center of the atom, but it's created from the core of a giant star. So this was postulated by two very awesome physicists. This is in 1934. They wrote a paper called Cosmic Rays from Supernova. And in this paper they wrote the following paragraph. In addition, the new problem of developing a more detailed picture of the happenings of a supernova now confronts us. With all reserve, we advance the view that a supernova represents the transition of an ordinary star into a neutron star, consisting mainly of neutrons. Such a star may possess very small radius and extremely high density. And one very startling fact I find about this is that this paper was written in 1934, but the neutron itself was only discovered in 1932. This kind of shows you the sort of minds of the time in this great era of physics. People discovered that the neutron was at the center of the atom. People who were working on a completely different phenomenon, and within 2 years you have a theory of neutron star. And so this is going to be talked about next week. And so while this happened in 1934, it took 30 years. So this is just, I'm praising this amazing work, but this is just a crazy object that they've written down that nobody saw. And it took 30 years for people to be confronted by a phenomenon, and the solution to that phenomenon is the neutron star. And so the pulsars were discovered in 1937 by Jocelyn Bell Burnell, working with her supervisor, Anthony Hewish, using this telescope, which is called a 4-acre array. It's the Mullard Observatory in Cambridge. And this is essentially a bunch of antennas all wired up. And it's not a moving telescope. It just sort of is a bunch of radio antennas that sits there, and as the Earth moves, it just scans over the sky. I understand that the material used to make this telescope was actually salvaged from World War II barbed wire infrastructure that was lying around. So the pulsar was discovered by the PhD student at the time, Jocelyn Bell, who was from Belfast, Northern Ireland. And it comprised of 2,448 dipole antennas. And a quote from Bell at the time was, "By the end of my PhD, I could swing a sledgehammer," because that's what you do with grad students. You put them out there to hammer poles into the ground. And Anthony Hewish was using it to study scintillation of radio galaxies. So that is that the signal from radio galaxies, the radio signal from galaxies, it passes a lot of material on the way, including material from the solar wind. So the Earth is living in the bath of the solar wind. And so this material from our own sun has an effect on radio signals from galaxies. And so he was studying that. They didn't know anything about pulsars at the time. And so Jocelyn Bell showed her advisor something like this. So what we're looking at is sort of a recording, so you can imagine like an arm with a pencil on it and a piece of paper that goes on a roller, and the pencil moves up and down. And so what Jocelyn noticed was that at exactly 1920 hours, so at exactly the time of 1920, 20 past 7 in the evening, she always would see this little, what she called scruff. The word was scruff. And it looked very much like this signal here, which would come all the time. It's just interference. Lots of stuff makes radio signals that a telescope like this can pick up. Your car motor, an electric fence, lots and lots of things can make a radio signal. And so they would see these interference all the time. However, what Jocelyn noticed was that this same signal was showing up at the same time every single night. How can that be? So they went around to some of their friends, and they got a faster strip chart recorder. That is, the pencil that sort of squiggles on the piece of page, they got the page to move faster. And what they recorded was these signals, familiar from what we showed earlier in the lecture. And underneath here, this is a clock. So this is telling them exactly kind of what I guess 4 times a second or something like that. And what you'll see written, so this slide, by the way, was shown by Jocelyn Bell when she gave a talk when I was at McGill in 2007. And she pointed out that she had written the words on her notebook, on her logbook, the words LGM. Can anyone hazard a guess what LGM stands for?
Green Man.
Little Green Man. So, for a while, they were asking themselves, how can it be that there's a radio signal like clockwork coming from space, like a Morse code from an alien? So for a while, they seriously had to grapple with the fact that maybe they were intercepting radio signals from aliens. So this is an excerpt from Anthony Hewish's Nobel Prize acceptance speech. So he writes, "To my astonishment, the readings fell in a regular pattern to within the observable uncertainty of 0.1 seconds, showing that the pulse source kept time to better than 1 part in 10 to the 6. I could not believe that any natural source would radiate in this fashion, and I immediately consulted astronomical colleagues at other observatories to inquire whether they had any equipment in operation which might possibly be generating an electrical interference signal at a sidereal time near 19 hours 19 minutes. Having found no satisfactory terrestrial explanation for the pulses, we now begin to believe that they could be generated by some source far beyond the solar system, and the short duration of each pulse suggests that the radiator could not be larger than a small planet. We had to face the possibility that the signals were indeed generated on a planet circling some distant star and that they were artificial. I knew that timing measurements, if continued for weeks, would reveal any orbital motion of the source as a Doppler shift, and I felt compelled to maintain a curtain of silence until this result was known to some certainty. Without doubt, those weeks in December 1967 were the most exciting of my life." So this shows how clever this man is. He thinks to himself, okay, if we're dealing with aliens, they're probably living on a planet, and this planet is orbiting their sun far away. And so if they have a radio loudspeaker pointed at the Earth, pumping its Morse code at us, then sometimes as their planet, as they orbit in their planet and it arrives closer to us, those signals will arrive closer, and as it moves away from us, those signals will move away from us. So I'm almost at the end, we can ask questions. So he looked for this signal, and he found a Doppler signal. But the signal he found was the Earth's motion. Okay? Because the Earth is moving closer to the pulsar, and the Earth is moving away. So in all of this pulsar analysis stuff, you have to take out the effects of the Earth as it orbits the Sun. So they did not find a Doppler shift in the data, and one entirely consistent with the Earth's motion was found. That convinced Hewish and Bell that the signal was not made by extraterrestrials, and they published their historic paper, Observation of a Rapidly Pulsating Radio Source. The abstract of this paper writes, "Unusual signals from pulsating radio source have been recorded at the Muller Radio Observatory. The radiator seems to be coming from local objects within the galaxy and may be associated with oscillations of a white dwarf or a neutron star." So here they were postulating the idea that we're dealing with oscillations, vibrations, not rotation. So the pulsar that they found had a period of about 1 second. And so there is a type of star called a white dwarf, and a white dwarf does have pulsations that can be very fast. It's theoretically possible that you can have pulsations of about a second. But once they started to find more of these pulsars, especially ones that have millisecond periods, then they knew they couldn't be dealing with vibrations. They had to be dealing with rotations. And shortly before they submitted their paper, they discovered a second pulsar. This is an excerpt from Jocelyn Bell. "I switched on the high-speed recorder, and there it came, blip, 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 blip. Clearly the same sort of stuff, and that was great. It was really sweet. I finally scotched the little green men hypothesis because it's highly unlikely there's two lots of little green men on opposite sides of the universe, both deciding to signal a rather inconspicuous planet Earth at the same time using the same daft technique and a rather commonplace frequency. It has to be some new kind of star not seen before, and that cleared the way for us to publish and go. Okay? So as I said before, Anthony Hewish and Martin Ryle won the Nobel Prize in Physics in 1975 for their pioneering research in radioastrophysics. Ryle for his observations and inventions, in particular the aperture synthesis technique, and Hewish for his discovery, for his role in discovery of pulsars. And the exclusion of Bell in the prize has been a point of controversy.
Political bastard.
I was going to ask. I was going to ask you about the second bullet up there.
So anyway, that's all I have to say today. But I have a schedule for what we're going to talk about in the following weeks. So what you've heard is setting the stage. Next week we're going to hear from Death Comes New Life, which is how the supernova happens and how pulsars are born. Then I'm going to tell you how they emit. Then I'm going to describe tests of Einstein's theories using pulsars. May 2nd, I'm going to talk about weirdos, things called rats, giant pulses, and magnetars. On May 9th, I'm going to talk about the work that I do, which is on gamma ray pulsars. Then on the 16th, I'm not exactly sure what I'm going to tell you, but it's going to contain certainly what's hot right now. What is the pulsar community talking about right now? Then we're going to talk about building a gravitational wave observatory from pulsars. And then the last lecture is going to be hoping for gravitational waves with an instrument called LIGO. So thank you very much.
Can you bring a slide number 2?
Hold on now, I have...
Yeah.
I want to know if I was first. I interrupted you, sorry. Okay. Did she get any recognition?
Joshua Bell has won many awards. And she has said, perhaps cheekily, that if you get the Nobel Prize, nobody else gives you anything else because they feel they can't compete. So actually, Joshua Bell has won many, many awards, many more than Anthony Hewish, but not the Nobel Prize.
Yeah, me. No, it's me. It's me. Do neutron stars are always pulsars? I mean, a neutron star is also a pulsar.
So, isolated neutron stars that are not pulsating, like through a radial beam, they're very, very difficult to detect. So there are some sources, neutron stars, that have been observed that are not pulsing, but we see them because they have a nearby companion, and that companion is materials falling onto them and heated up. So yes, there are cases where two of things could be happening. They don't emit at all, or the emission is not beamed in the direction of Earth, and we would need to be at another planet to see it. All right, now.
I just want to know, are there any observations of pulsars in companion with a black hole or anywhere near an event horizon?
I don't believe... Oh, okay, so the question is there examples of a pulsar orbiting a black hole? And this is, maybe I shouldn't say this, but I would consider this to be one of the Holy Grails, to find a pulsar that orbits a black hole, because it would allow us to measure. So one of the reasons why I like pulsars, it's a point I wanted to make throughout the talk that I didn't make, so I'm going to say it explicitly now. It's one of the things I find incredibly interesting and compelling about pulsar research. Astronomical research is generally observational science. It's not a laboratory science. On Tuesday, we point our telescope at the sky and we see what we see, and on Wednesday, it might not be there again. Whereas if you're in a laboratory science, on Tuesday, you can twiddle your knobs in the lab and measure something, and then on Wednesday, you can do the same. And then you can call up your buddies in the lab down the street and say, hey, we've been twiddling our knobs like this, will you do it too, and see what you get? And so if you have a laboratory system, you can be very, very controlled in your experiments. When you have an astronomical observation system, nature does what it wants, and we just have to be lucky enough to see it. So if nature happens to hand us something that behaves very regularly, that behaves very predictably. This allows us to get into problems that we can't ordinarily get into. And pulsars do that. There is absolutely nothing better than a very heavy clock in space. For gravitational studies, a heavy clock in space is God's gift. And so that's why I call it nature's timepiece. They're very heavy, they're very regular. And so if you can find a pulsar orbiting a black hole, then you can do great black hole studies. But so far, we have not. All right.
Okay, is there a theory? I know observationally you've discovered that pulsars are between 1.4 and 2. So is the theoretical reason to
Sure. Yes, there is. There is a theoretical reason, and that is the. Oh, is there a theoretical reason why a neutron star would live in this range of masses between 1.4 and 2 solar masses? Why not heavier neutron stars? And so the problem is that, and what we'll talk about in future lectures is, what's holding a neutron star up is called neutron degeneracy pressure, which is a sort of a quantum mechanical effect that happens. And when you have more mass, you are stronger than neutron degeneracy pressure. That can no longer provide a pulling force against gravitational collapse, and you get a black hole.
Could I ask a real low-level question?
Please.
Are any of these guys near us?
Are any nearby? Sure. I mean, so
Congress.
okay, so there. All the pulsars that we know of are in our own galaxy, except there are some that are in the Magellanic Clouds. So they're local. How local? They can be, you know, half a kiloparsec or even closer.
So is there a possibility that maybe one of these things can
Wipe this out.
yeah, be near us?
No,
I mean,
not
is it a star just kind of
No. I mean, we have nothing to worry about. I mean, they are very stable, small, distant objects. The supernova explosion, that might be something we might want to worry about, but even then, that's not very, very likely at all. I should say that our sun will not make a neutron star. So when our sun runs out of fuel, and what we're going to talk about in great deal next week, is what's happening inside a star like our sun is that the radiative outward pressure and the gravitational pressure are in equilibrium. And this is called a star that is in this kind of equilibrium is in what's called the main sequence. And if you have a giant star, at some point gravity is going to win. It's going to beat the radiation pressure out, and it's going to collapse. And the only thing that can stop it collapsing is this thing I described as neutron degeneracy pressure. If you beat neutron degeneracy pressure, you get a black hole. Our sun, however, is never going to. It's going to sort of die slowly, that it never gets off this equilibrium. We'll stay on this equilibrium for the rest of its life.
Thank you.
All right. Now I need help. Who was next? Be honest. Who was next? I'm gonna go for you, sir. Yes, please.
What about the asymmetry? You showed the guitar slide, which is transverse. Can you detect asymmetry from a neutron star that's pointing towards the Earth?
So the question is, can we detect the asymmetry of a neutron star pointing? So I think you're talking about the motion of the neutron star towards us. Is that what you mean? Yes. So one of the things which we're going to talk about in other lectures is, when you have a radio telescope and you observe these pulses, you have to figure out what's going on. Is it in a, you have to take away the fact that the Earth is rotating and the Earth is orbiting the sun and this source itself is moving, and perhaps it's moving in a binary system. And so all of these possible things that would affect the time of arrival, all of these things have to be accounted for in order to make a nice pulse profile that you see in that picture. And so how the astronomy community does it is they scan all of these places in the parameter space. They look whether is it orbiting faster or slower, is it slowing down, is it orbiting, is it moving. All of these things are things that they search in order to find the most sharp, the cleanest measurement. And then once you find that, then it should be very stable. If you have a pulsar that's moving across at high speed and you don't account for that, then over time you'll start to see your pulsar seem to drift and not look as sharp.
But the pulsar itself is asymmetrical, right? Its formation.
So the neutron star, is more or less a circle, more or less a sphere, and its motion is along the sky in some direction, and so
I see.
it's not. Have I answered your question? All
I
right.
think so.
Yeah. In the slide number 2,
Uh-huh.
your two descriptions, they don't complement each other, they are contradictory to each other. When the neutron star is rotating, it's also recessing. And that's why, not because it's rotating this way that it's going like that, it's because it's going like this.
It's not a precession. It is that the beam is not necessarily aligned with the rotation axis.
Why?
That's right.
Why?
Because
That's heavy.
So basically our own Earth's magnetic north is not the same as rotational north. There is no particular reason why the orientation of the magnetic field has to be exactly aligned or anti-aligned or co-aligned. There is some angle. And so so you were dealing with a star that is spinning perfectly on an axis, and then the beam comes out, and the beam doesn't have to come out straight, it can come out, at any angle in between. But then it goes around like this, and so if I'm anywhere in the sky, like the Earth is anywhere in that place in the sky, you'll see this pulse. But if you're in that place in the sky, you won't see it.
so slides 2 show that the two graphics are not consistent if you look it up.
Okay.
It shows you what you described in the graphic, but in the video, it's just showing something else.
So I'm also interested in your first cartoon with the beam rotating. So I assume that our pulse detection is a detection of a massive number of photons at roughly the same time. And with a view towards trying to integrate some of what you said with what we've heard about quantum mechanics in other lectures, I had two questions, one of which sounds like you're going to devote a whole lecture to. Just trying to get some concept of one of those photons. The first is, how does a neutron emit one? Which, if you don't want to comment on now, I'll come back for that lecture. The second one is this. So we're told, at least I think, as far as I comprehend, that when there's an emission of a single photon, quantum mechanics treats it as a spherical propagation of plane waves until there's a detection at a measurement when there's some mysterious event, which I've heard called wave collapse, and more lately decoherence of the wave function. And how did that all happen to make a beam go out that is consistent with that kind of quantum mechanical destruction?
So that is a very good question. And all I can say is that the situation you are describing about how we describe a photon as a sort of a wave that is then measured and the wave function is collapsed when we measure it and so on, that is happening to every single photon that exists. The photons that are hitting your eye right now, that is exactly happening right now. So what has happened? So the theories that we need to describe quantum mechanics and explore photons in the photon sector and that sort of theoretical physics, which uses quantum mechanics to explain all of that. That explains how photons behave. And the underlying description of how the waveform is collapsed and those quantum mechanical descriptions, those descriptions in the end return what it is that we measure always. Anyway, they resolve into the normal understanding of photons, that a photon arrives, leaves one place and is detected in another place. That happens. The description of how that happens, if you want to describe how it is that a photon leaves one place and arrives in another place, whether it be, bouncing off my shirt or off that light bulb or whatever, in order to describe that, you need quantum mechanics to describe that. But you don't need the understanding of quantum mechanics is not necessary for you to understand that a photon leaves one place and goes to the other. You can just say that. That does happen. That's what happens. The reasons why it happens in the underlying theory require quantum mechanics, but that isn't necessary. That isn't a necessary detail that complicates pulsar observations or stellar observations or your observations of the television set.
But in terms of the...
I need to move on. I'm sorry.
Would you comment briefly on the wavelengths at which the beams are emitting?
So the radio wavelengths that we observe, these are centimeters and meters in size. But we also observe them at optical wavelengths, which is nanometer wavelengths, and then X-rays and also gamma rays too, which is like 10 to the minus 12, 15 meters. So yeah, so they are seen most often in radio, which is centimeters to meter wavelength. But yeah, the higher energy emissions, it's very, very small wavelength radiation.
Have you found any binary pulsars?
Have I found
that has any power?
So,
in other words, you start out with one pulsar, the companion star, that also
is a pulsar. So the question is there a binary pulsar? Is there a pulsar out there that orbits another pulsar? And I don't want to tell you the answer to that, but I should tell you to keep coming to the lecture.
Neutron stars, they don't have any nuclear reactions going on inside.
Correct.
So where does the energy come from? The stars generate radiation because the nuclear reactions are going on. Where do we get this energy?
So the energy we see comes from the rotation. They are rotating, they're like a flywheel, they have rotational energy. And that rotational energy powers the emission levels. And those are called rotation-powered pulsars. There is also pulsars, accretion-powered pulsars, which are powered by the accretion onto them from a companion. So that is that the matter is falling onto the companion. And then there is a third, which will be in the weirdo section, and they're called magnetars, and they're powered in a different way. Go ahead.
Could you be seeing the pulse with every half rotation if the beam is coming out?
Sure.
And how would you know?
How would you know? So, you can measure other properties about the pulse. Its rising edge, its falling edge, also its polarization. They are polarized, and the polarization changes in different parts of the beam. And so if it was the case that you had two beams that were exactly separated by 180 degrees and spinning around it, it's unlikely that they would have the identical polarization swing. And so one would smell different from the other.
Have any of those been found?
We see pulsars with very interesting beam shapes, especially at optical and X-ray energies. We tend not to see just a single pulse, but a shape like that looks like many pulses. And so yeah, in higher frequencies radiation, we see a variety of awesome pulse shapes. Yeah.
In the traces that you show, what is the bandwidth?
What is the bandwidth? That I don't know yet. But I know that radio telescopes typically operate with, you know, maybe 200 or 300 megahertz bandwidth.
Oh, that was?
Yeah.
Because it would seem to me that if you have some inconsistencies or asymmetries, if your bandwidth is short enough, you would be able to pick that up.
So what we will talk about at other lectures is that typically the radio telescope that these are observed at, that's exactly right. It measures things in many, many different bands and then adds them together. And so you definitely see evolution of the pulsar shape in the different bands.
Are you using Fourier?
Yeah.
Okay.
You mentioned pulsars that accrete from a companion and level the maximum mass for accretion. Does that mean that a pulsar would either blow apart or collapse? And are these observable occurrences?
So I don't know that we've ever seen typically the situation is the other way around. That the mass loss of the companion star is a far more bigger deal to the companion star than whatever mass gain the neutron star is gaining. So the neutron star perhaps is gaining in mass. It might be gaining angular momentum. It might be gaining angular momentum by the thing falling off. But typically it's the star who's going to be, perhaps through this mass loss process, will no longer be able to sustain the gravitation. Its gravitational infall will not be sustained by the radiation pressure. And so typically it's the companion that is in trouble, not the neutron star.
Yeah, I was wondering if you said the neutron star is like a giant neutron. Has that led to any discoveries about neutrons themselves?
So I don't know if I said it was like a giant neutron. It was more like a giant ball of neutrons. And this is actually not what I'm going to talk about in this series of lectures. But it is a very active area of study, is actually the interior of the neutron star. The interior of the neutron star is a very crazy place. It's at densities that we can create. And so it is possible that we could learn about, we could use the inside of a neutron star to learn about the like nuclear physics that we can't recreate on the Earth because we can't make something as heavy as a neutron star. And there is a little bit of feedback. There is a little bit of knowledge that we've learned from neutron stars that perhaps can inform nuclear physics. But it's very, very hard to get information out of a neutron star. One of the things that we observe in neutron stars that will be, again, something we'll talk about in the coming few weeks, is that they undergo what's called glitches. That is, something happens that sort of causes the rotation to freak out a bit. And so the rotation slows down for a second and then might recover and be spinning again at a different level. And what we believe these glitches have something to do with what's happening inside the neutron star. And certain glitch behavior is used to infer that. But that isn't really what I'm going to talk about that much. But yeah, this is certainly an active area of research.
Maybe I missed something, but is it pure neutrons? Is that possible? And what happens to
protons?
The protons are like?
No, it's not entirely neutrons. There is a mix of other stuff in there. A small few protons and a small few electrons are necessary to keep the mix just right. But it's overwhelmingly neutrons.
Yes, please. It's amazing that this star has such equilibrium with such incredible forces going on. I mean, it has all this magnetic force, the mass. You haven't mentioned the temperature. And I just wonder if you could talk about the kind of equilibrium that makes all this possible. I mean, I don't know that much about physics.
Sure.
It just seems amazing.
So quantum mechanics is an amazing field, for sure. And what we find about nature, what quantum mechanics tells us about nature is that there are certain configurations that are allowed and others that are not allowed. Like the atom, when we look at the hydrogen spectrum of an atom, tells us that the electron, when it orbits the nucleus, it orbits it in very precise places and not in other places. It can't go there. Nature doesn't allow it. So nature, when you're dealing with very, very tiny quantum mechanical situations, nature forces very particular rules on where you can be and where you can't be. And so it is this bizarre phenomenon of nature that tells the neutrons how they're allowed packed together. And they can't pack in any other way. And so because if you think about how these neutrons are packed together, and you have some force of gravity, some other force that's trying to pack them smaller, there's nowhere smaller for them to go. They can't go there. And that is the equilibrium right there. You have this, what's called neutron degeneracy pressure, which I know I've said a few times, and I hope next week you'll understand better what that is. But at the end of the day, it's just a fact of quantum mechanics that certain states are allowed, and outside those states, they're not allowed. And so the lowest possible energy state you can put the neutrons in, they can't go any lower than that. And so that is the reason why there is this equilibrium. As for the temperature, so the neutron star itself doesn't really radiate. Doesn't like the surface of a normal star, which has a fusion going on and so on. There is no fusion going on, so we don't have a hot surface of a star like we think of with a regular star. And the emission that we see in that, what's going to be talked about in lecture 3, I believe, is where does the emission come from? And the emission doesn't come from the star itself. It comes from a region around the star, a nebula, that is caused by the magnetic field. The spinning magnetic field creates a nebula. And this nebula is where the radial beam comes from, and the other emission. So the only time we see emission from the surface of the star is in the case where we have another star nearby. And that other star can dump material on it. That's the only way we can get hydrogen or any of that stuff that is normally in stars. That's the only time we can get that onto a neutron star and have any emission. And so in these cases where we see emission from the neutron star, it's a special situation where we have a donor companion donating mass. And it's that mass that we see in the star-like way, not the neutron star itself.
So there's no such thing as a pure neutron star. They're all kind of got junk.
No. There are pure neutron stars, but that we will not see through emission from the other mass. We will only see it through the what's called a magnetospheric emission, the nebula that comes off the pulsar.
Can neutron pulsars rotate at speeds other than the ones we observe?
So this is a great question, and the question is, can neutron stars? And so what we have with neutron stars is they're born with a certain speed, and that speed is to do with the size of the mass of the original star and the rotation that was happening. And basically, they get slower. So the younger ones, all the ones that are 1,000 years old or 2,000 years old, those are the ones that are going fast. And then they lose their energy. And they slow down. Now, a very remarkable thing can happen when you have a companion. And that is that the companion can give you angular momentum. You can be in a situation where through the orbiting of a companion, you can actually gain angular momentum. And then you get a different class of pulsar, what we call millisecond pulsars. These are pulsars that have periods that are very, very fast, like the fast one that Jason found in Tarzan 5, the globular cluster. And that is what's called the recycled pulsar. So this is a regular pulsar that was born with a regular speed, that then got a companion or had a companion when it was born, and that companion donates angular momentum and spins him up. And so when we look at later on in other weeks, we're going to explore the periods of pulsars, and through that exploration we will see the different evolutionary paths. I think I don't want to go any further today. I want to give you some stuff where please from